3.2, number 37. We want to prove that, well, we're going to let A equal 1101, and we want to prove that A to the n is equal to 1n01 by induction. Just so that you have an idea of what the heck that means. By induction. Okay. First, note that the result is true when n equals 1, right? Because a to the first power is a, which is 1101. Okay? And what you're doing there, this is what I like to call the base case, okay? Or the first domino. When you do a proof by induction, there's two things you have to do. You have to have the first domino taken care of. And then the other step is this. The induction step. The induction step is this. You assume the theorem is true when n equals, let's say, k. I'll use capital K. And then show that this implies the theorem is true when n equals k plus 1. And see, k is a variable. It doesn't matter what k is. So we're going to assume the theorem is true when n equals k and show that this implies the theorem is true when n equals k plus 1. Okay? So if you think about how I've been doing proofs, I've usually been writing the given information closer to the top, and then what I'm trying to prove, well, somewhere down on the bottom of the page, right? So let me do that. Down here at the bottom, well, we're going to have a to the k plus 1 is 1 k plus 1, 0, 1. Because that's what I hope that I get that at the bottom, right? I don't have that yet. So here I go. I'm going to try and do the induction step. So now, assume we know that a to the k power is equal to 1k 0, 1. Let's assume we know that. Now we checked the first cases up to n equals k. All right? And we compute, well, I'm trying to get this equation here at the bottom. So I'll write down the left-hand side, a to the k plus 1. Now what does that mean? Well, that means a times a to the k. By definition, right? That's what it means. It means you're going to multiply a to the k by a one more time. That equals, well, let's work it out, 1101 times, and we're assuming that a to the k equals what? 1k, 0, 1. So now I have some work to do. When I multiply these two matrices together, what size do I get? I get a 2 by 2, so that's good. I hope I get that. I guess a question I have is, when you did the quiz today, how did you guys do the multiplication at the top? Did you guys do dot products or did you do columns? Looks like different people did different things. I'll do dot products here. I'll do the dot products. So I'm going to do equals, and I'm going to work out what these dot products are, right? So the first dot product, right, where does this come from? It comes from row 1 and column 1. So this is going to be 1 times 1 plus 1 times 0, right? Which equals 1. So we got the first piece. You guys with me? Second piece, I'll do the 1 times 1 times the second column, right? And so this is 1 times k plus 1 times 1, and sure enough, that gives me the k plus 1. And you could check the next one, 0, 1, 1, 0. You guys with me? It all works. It all works very nicely. The last one would be 0 times k plus 1 times 1, which is 1. Okay? And we've done it. This proves a to the n equals 1n, 0, 1 for any positive integer n. It's like you get all those for free. So that's kind of a cool thing to know about.
Does it work for 0 too?
That's a good question. Does it work for 0? Can you take a matrix to a 0 power?
You get the identity.
And you get the identity? I guess we could define it that way. It's interesting because then what about the negative first power? Well, we're going to hold off on negative first, and we're going to actually use that notation to talk about matrix inverse. So I'm hesitant to use the 0 power in matrices. But I've seen this done. I've seen this done. One of the problems is that not every matrix has an inverse. So I'll show you guys that. Where's MATLAB? Here we go. If I go back to this, remember our matrix A we had before? So I could hit A caret 0. Let's see what MATLAB likes your idea, Chad. It gave me the identity. But if I hit A caret negative 1, well, let me try one more time. I think I need parentheses here is all that means. Oh. I didn't prove that. I'm just curious. Well, that's cool. I'm curious again. Now, hold off a second. What does that even mean? When you do an exponent of 1/2,
Square root.
in the world of numbers, that means square root. I'm just curious. I don't think it's well defined here. I'm just curious. Cube root of a matrix? Yeah, I think it's having trouble with fractions. That's my take on this. Interesting. I'll point out one other thing. B caret negative 1. What does that mean? Yeah, B was this matrix we had before. And you might remember b squared was very interesting. That doesn't happen in the world of in the world of numbers. Because we use a property all the time in the world of numbers that I want to remind you of. We like to use this property that if a times b equals 0, right, then what has to be true? A equals 0 or b equals 0. This property is not true for matrices. In the mathematical term, we say that 0 divisors exist. You could have things that multiply to give you 0 that are not, you don't have one of them being 0. So in the example I just showed you, b times b.
Zero divisors?
Yeah, they're called 0 divisors. I don't think that word's in your book, but that's the name typically used for them. All right. Well, it's break time, guys. We're going to pause here. If you have homework, of course, you can leave it on the table on your way out. I think when we come back, I'm going to put you guys in the groups we were in last week. Okay? So we'll go from there.